Question 19. So I'm going to go through and just show you how to approach this type of question. It's a very theoretical procedural question. There's not a lot of context to it. So if you read the question and you think about it thoroughly, then it's not too bad a question to go about. So first of all, it says show that the tangents drawn at the point of inflection of these point of inflections of this function intersect at that point. Now the first thing you may consider doing is sketching this on your graphics calculator. You'll see it's a quartic. It will have 2 points of inflection. Remember, the 2 points of inflection are where we have maximum or minimum gradients, and the gradient changes, so the rate of change is changing direction. So you get that, I can't really show you now, but you get that hand movement where your gradient is getting more and more negative, and all of a sudden it starts to head in a positive direction. And you can do that with your hand to show that. But point of inflections occur, so the point of inflection occur when d squared y dx squared is equal to 0. So we're looking for the turning point of the gradient function. So therefore we're looking for when the second derivative is equal to 0. So let's find the second derivative. Y is equal to x squared minus 1. I think in this case it's pretty reasonable to expand these brackets and make it a simple polynomial. So y dash is equal to 4x cubed minus 2x, and y double dash is equal to 12x squared minus 2. Now I'm going to let y double dash equal 0, and that gives me 12x squared minus 2 is equal to 0. 12x squared is equal to 2. X squared is equal to 1/6, which is 2 over 12, and x is equal to 1 over the square root of 6. So I want to keep this exact where I can. Now in a bid to stay close to the original question, I'm going to use, actually x squared is equal to plus or minus 1 over the square root of 6. Remember, we have a point of inflection. I'm going to use, go sideways on my screen here. So if x is equal to that, then I need to find not only the gradient at this point, but I need to find the original function value at this point. So I start with at x equals 1 over root 6, y is equal to 1 over root 6 squared, 1 over root 6 squared minus 1. So that's from our original function here. And I get this. It's equal to 1 over 6 times 1 over 6 minus 1, which is equal to 1 over 6 times negative 5/6, so it's negative 5 over 36. So the coordinate is 1 over root 6, comma, negative 5 over 36. And over here I'm going to also run through the at x equals negative 1 over root 6. But I probably won't show the same amount of working. Hopefully you can get to, when you square both, and you'll end up with exactly the same value, 5 over 36. So therefore we have our second point is negative 1 over root 6, comma, negative 5 over 36. And at x equals 1 over 6, we have y dash, which is our gradient, is equal to 4x cubed minus 2x, which in this case will be 4 times 1 over root 6 cubed minus 2 times 1 over root 6. So this is going to be a little bit trickier to play around with. Still not too bad. So I end up with 4 over 6 root 6 minus 2 over root 6. I rationalise the denominators to give me 4 root 6 over 36 minus 2 root 6 over 6. I make 4 over 36 into 1 over 9, 2 over 6 into 1 over 3. I'll make that 3 root 6 over 9, and it will give me root 6 minus 3 root 6 all over 9, which of course is equal to negative 2 root 6 over 9. So there's my simplified version there, and of course my y dash over here is going to be similar, not quite as easy, so I'll do a little bit of working but not too much, mostly make sure that I do the right thing. 4 times negative 1 over root 6 cubed minus 2 times negative 1 over root 6. So it's going to give me the same thing, except this time my first term will be negative, my last term will be positive. And that's quite nice because that means it'll come out as positive 2 root 6 over 9. So they're my two gradients. Now continuing to follow this vertically, it means that here we have y equals negative 2 root 6 over 9 x plus c, and this is at the coordinate which I got earlier, which is 1 over root 6 comma negative 5 over 6, so negative 5 over 36, and that gives me negative 5 over 36 is equal to negative 2 root 6 over 9 times 1 over root 6 plus c, and that's quite nice because those 1 over root 6's cancel. So then that gives me c is equal to negative 5 over 36 plus 2 over 9, and that's equal to 3 over 36, which is equal to 1/12. And that's quite nice. And over here, same thing again, I take this down, I get y is equal to 2 root 6 over 9 x plus c, and at the coordinate negative 1 over root 6 comma negative 5 over 36, I get negative 5 over 36 is equal to 2 root 6 over 9 times negative 1 on root 6 plus c. The root 6's cancel out. I end up with c equals negative 5 on 36, but this time again plus 2 over 9, so again that's equal to 3 over 36, which is equal to 1 over 12, and so my two functions are y equals negative 2 root 6 over 9 x plus 1 over 12, and over here y equals 2 root 6 over 9 x plus 1 over 12, and I see that the gradients are the same but one's positive and one's negative. That's interesting, but more importantly they have the same y-intercept. So if they've got the same y-intercept, then necessarily that must be the point that they meet. And so we can clearly state here they meet at 0, 1 over 12, which is also their y-intercepts. We go back up to the question, seems like a long time ago now, and that's what was asked of us, to show that they intersect at the point 0, 1 over 12.